Now in this lecture we talk about the limit of a sequence. A sequence is a set of numbers, and actually a sequence can be finite, like this sequence that consists of only 3 terms, but the sequence could be also infinite, like the set of the natural numbers that consists of infinite terms. In this lecture we talk only on sequences that consist of infinite terms, like the set of the natural numbers. So actually the limit of a sequence is the value that the terms of a sequence tend to. Okay? And it is often denoted using the lim symbol. So here we write down that the lim is a variation for limit of sequence a(n) when n tends to infinity So here n is the index of the sequence. For example, when the index n equals to 1 in this sequence, the set of the natural numbers for a1, the value of the term is 1. When the index n equals to 2, then the value of the second term, a2, equals to 2. And when the index n equals to 3, then the value of the third term, that's to say a3, equals to 3. So n is the index of the sequence, and a is the value of the term that is index is n. So if the limit of the sequence an when n tends to infinity exists, then that is to say sequence an converges to the limit L when n tends to infinity. Then so if lim an when n tends to infinity equals to L, L belongs to the natural numbers. That is to say, when the limit of a sequence is finite, then we'll say that sequence an is convergent. Okay? If a sequence is convergent, then it will have only one limit. So if a sequence has two limits, then it doesn't have a limit at all. It doesn't converge at all. Therefore, if for example we have sequence Bn that doesn't converge, then we define sequence Bn as divergent sequence. Okay. Actually, the limit of a sequence is said to be the fundamental notion on which the whole of mathematical analysis ultimately rests. So what is the definition of a limit of a sequence? So actually, a number L, here L belongs to the real numbers. A number L is the limit of sequence AN and n tends to infinity. Yeah, the limit of sequence AN when n tends to infinity is equals to L, and L belongs to the real numbers. Only if the numbers in the sequence become closer and closer to L. I repeat again, the limit of sequence AN when n tends to infinity is equals to L. L is a finite number, and the limit is a finite, so that is to say L belongs to the real numbers. Only if the numbers in the sequence become closer and closer to L. Okay? So this is the first way to write down that the limit of sequence AN when n tends to infinity equals to L, or we can write down the same thing in another way. Here we can write down that AN, if the right arrow, equals to L. So those are the two methods to write down the same thing. That the limit of sequence AN when n tends to infinity is equals to L. So only if the following condition holds, we will write down that the limit of sequence AN when n tends to infinity is equals to L. And the condition that must hold is as follows. So each real number for each real number epsilon that is greater than 0, that is to say epsilon is a positive number, there exists a natural number capital N such that for every natural number n that is greater than capital N, we will get that the absolute value of AN minus L is smaller than epsilon. So only if this condition holds, we can say that the limit of sequence AN when n tends to infinity is equals to L. Again, L belongs to the real numbers. That is to say, we are talking here on finite limits. Repeat again, the condition that must hold is as follows. For every epsilon that belongs to the natural numbers that is a positive number, it is greater than 0, there exists capital N that belongs to the natural numbers, and for every natural number n that is greater than capital N, we will get that the absolute value of AN minus L is less than epsilon. So the meaning of this condition is that the terms of sequence AN are close to the limit L up to epsilon. So graphically we can describe the condition that must hold as follows. Here, if this is L, that is the limit of sequence an when n tends to infinity. Then we have the environment of L. The environment of L starts from L minus epsilon and ends at L plus epsilon. So this is the environment of the limit L. Okay, this is the environment of L, and the environment starts from L minus epsilon, but the point L minus epsilon itself is not included in the environment, and ends at point L plus epsilon, but the point L plus epsilon itself is not included in the environment of L. Okay? So, what is the meaning of this condition that must hold? The meaning of this condition is that from the index n onwards, all the terms of sequence an must be in the environment of L. That is to say, they must be located inside those two brackets. Okay? And because of the fact that until the index n we have fixed terms or finite terms that maybe not obey to this condition, but because of the fact that from the index n onwards we have infinite terms of sequence an that obey to this condition. That is to say, we have infinite terms of sequence an that are close to the limit L up to epsilon. That is the meaning of the condition that must hold. Okay, and that is the reason, because of the fact that we have infinite terms in the environment of L, that is the reason that the limit of sequence an when n tends to infinity is equals to L. Okay? I'll repeat again that in order that the limit of sequence, this example is sequence an will be equal to L, infinite terms of sequence an must be located in the environment of L, or infinite terms of sequence an must be located between those two brackets. Okay? So, symbolically, we can write down that condition that must hold in order that the limit of sequence an when n tends to infinity will be equal to L as follows. For every epsilon that is greater than 0, there exists, this is the sign of exist, capital N that belongs to the natural numbers, and for the natural number n, or for any natural number n that is greater than capital N, we will get that the absolute value of an minus the limit L is less than epsilon. Okay? That is the condition that must hold in order that the limit of sequence an when n tends to infinity will be equal to L. Okay? As I already mentioned before, it means that from the index n onwards, we will have infinite terms of sequence an that obey to this rule. That is to say, we have infinite terms of sequence an that are close to the limit L up to epsilon. Here, inside the environment of L, that is to say, inside those two brackets, we have infinite number of the terms an, and for that reason, the limit of sequence an when n tends to infinity is equals to L. Okay. So I can say on sequence an that converge to the limit L, that sequence an is a convergence sequence, and L is the only limit of sequence an. Otherwise, if sequence an has more than one limit, then it is not convergent, but it is a divergent sequence. So in the next step, I will present to you an example for a sequence that the limit of the sequence when n tends to infinity is equals to 0. So here we are talking about the sequence an that is equals to 1 over n. So what are the terms of sequence an? When the index n equals to 1, so the value of the first term is 1 over 1. When the index n equals to 2, that is to say a2, the value of the second term is 1 over 2. When the index n equals to 3, then the value of the third term, a3, equals to 1/3, etc., etc. When the index n equals to 100, then the value of the 100th term, that is to say a100, equals to 1 over 100, that is 0.01. And finally, when the index n equals to n, then an equals to 1 over n. So it is very easy to see here that as n increases, the terms of the sequence are getting closer and closer to 0. Why? Because the first term is 1, the second term is 1/2, the third term is 1/3, the other term is 0.01. So as n increases, the terms of the sequence are getting closer and closer to 0. So we will assume that the limit of this sequence an equals to 1 over n when n tends to infinity is equals to 0. So we have to prove that the limit of sequence an equals to 1 over n when n tends to infinity is equals to 0. In order to prove it, we have to prove that the condition that must hold here indeed holds. So which condition must hold? The condition that must hold is as follows. Let epsilon be greater than 0 and for capital N that belongs to the natural numbers, that is to say, for capital N that is big enough, there must be n, the natural number n that is greater than, for every natural number n that is greater than capital N, we must get that the absolute value of 1 over n minus 0 is less than epsilon. So this condition must hold in order to that the limit of sequence an equals to 1 over n when n tends to infinity will be equal to 0. Okay? So actually I have to find out capital N, such capital N that will give us that the absolute value of 1 over n minus 0 is less than epsilon. So here the absolute value of 1 over n minus 0 is equals to the absolute value of 1 over n. Why? Because when you subtract 0 from anything, it doesn't change anything. Therefore we can cancel the 0. We cancel out the 0, so the absolute value of 1 over n minus 0 equals to 1 over n. And because of the fact that n is a natural number, that is actually a positive number, positive natural number, the value of 1 over n will be always a positive number. And we also know that the absolute value of a positive number equals to the positive number itself. For example, the absolute value of the positive number 5 equals to 5. And therefore, the absolute value of the positive number 1 over n will be equal to 1 over n. Okay? And we have to prove that the absolute value of 1 over n minus 0 is less than epsilon. Okay? So we actually have to prove that this inequality is true. That is to say, we have to prove that the inequality of 1 over n is less than epsilon. Okay? So we will multiply this inequality by n, and we will get that 1 is less than epsilon times n. Here we will divide this inequality by epsilon, and we will get that n is greater than 1 over epsilon. Here it is smaller than fighting again. We found out that n must be greater than 1 over epsilon. That is to say, the condition that must hold is actually this condition. So we have to find out such capital N that in such a way that this inequality n is greater than 1 over epsilon is true. So we'll choose capital N that is greater than 1 over epsilon, and therefore for any n that is greater than capital N, and according to our choice we choose capital N that is greater than 1 over epsilon. So here we choose n that is greater than capital N, therefore this inequality is true. And we choose also capital N that is greater than 1 over epsilon. Okay, so that is to say this inequality in total is true. So from this inequality we will derive that n is greater than 1 over epsilon. So in conclusion, we found out that if we choose capital N that is greater than 1 over epsilon, then we'll get that this inequality is true. That is to say, we'll get that n is greater than 1 over epsilon. Okay? And therefore the limit of sequence n equals to 1 over n and n tends to infinity is equals to 0. And as I already mentioned before, we have the right to choose n that is greater than capital N. So this inequality is true according to our choice. So we divide this two inequality by n, and we get that 1 is greater than capital N over n. Here we divide this inequality by capital N, and we get that 1 over capital N is greater than 1 over n. So we found out that 1 over n is smaller than 1 over capital N. Okay, and we have only found out that 1 over n minus 0, the absolute value of 1 over n minus 0 equals to the absolute value of 1 over n. And we already found out that the absolute value of 1 over n equals to 1 over n. And we just right now found out that 1 over n is smaller than 1 over capital N. Okay? So we can write here that 1 over n is smaller than 1 over capital N. So we'll focus on this expression 1 over capital N. Actually, if for example we have the number 1 over 5, so if we don't change the numerator, so we have in this a number in the numerator we have 1, so we will leave 1 as it is, and we only decrease the denominator for 5 to 4, That is to say, whenever you decrease the denominator of a number, then you will increase the original number. Here, 1 over 5 will become 1 over 4, and 1 over 4 is greater than 1 over 5. So from this example we can conclude that whenever you decrease the denominator, you will get a number that is greater than the original number. So here we'll focus on this number 1 over capital N. We will not touch in the denominator, so in the denominator we have 1, so we will leave 1 as it is, and we will only decrease the denominator. We have the denominator capital N. So here we will decrease the denominator, and we know that 1 over epsilon is smaller than 1 over n. So we will decrease the denominator from capital N to 1 over epsilon. Again, we know that 1 over epsilon is smaller than 1 over n, so when we substituted 1 over n by 1, when we substituted the denominator capital N by 1 over epsilon, actually we decrease the denominator, and when you decrease the denominator, you will get a number that is greater than the original number. That is to say, 1 over 1 over epsilon will be greater than 1 over capital N. Okay, exactly like in this example, when we decrease the denominator here in this number from 5 to 4, we will get here that the new number that we created here will be greater than the original number. Here we decrease the denominator from capital N to 1 over epsilon, and therefore this number will be greater than the original number 1 over capital N. And what is the value of 1 over epsilon? It is equals to epsilon. So in conclusion, we found out that the absolute value of 1 over n minus 0 is smaller than epsilon. That is to say, if we choose capital N that is greater than 1 over epsilon, we will get that the condition holds. Okay? So we can write down that we proved that for any epsilon, there is also the real numbers, and it is greater than 0, that is to say any epsilon that is a positive number, there exists natural number capital N. We choose capital N that is greater than 1 over epsilon, and for any natural number n that is greater than capital N, for any natural number n that is greater than capital N, we actually found out that the absolute value of 1 over n minus the limit 0 is smaller than epsilon. That is to say, if we choose capital N that is greater than 1 over epsilon, then the condition holds, and therefore the limit of the sequence an equals to 1 over n when n tends to infinity is indeed equals to 0. Why? Because the condition that must hold indeed holds. Okay? So until now we talked about the sequences that have a finite limit. So in the next step we talk about sequences that have infinite limits. That is to say, they have a limit in the broadest sense, and the limit is infinite. Okay, so in the next topic we will talk about infinite limits. That is to say, we are talking about sequences that have a limit in the broadest sense, and the limit is infinite. So a sequence an is said to tend to plus infinity when n tends to infinity. So the limit of sequence an when n tends to infinity is equals to plus infinity. That is to say, the limit of sequence an in the broadest sense is equals to plus infinity. Or we can write down the same thing in another way. Here, or we can write down that an with the right arrow that is equal to plus infinity. Only, so those are two different ways to write down that the limit of sequence an when n tends to infinity in the broadest sense is equals to plus infinity. So only if the following condition holds, we can say that the limit of sequence an when n tends to infinity is equals to plus infinity. Okay, and the condition that must hold is as follows: for every real number k as large as we would like, and k belongs to the as already mentioned, k belongs to the real numbers. For any big number k as large as we would like, there is an natural number capital N, and for every natural number n that is greater than capital N, we will get that an is bigger than k. Okay, so this is the condition that must hold in order that the limit of sequence an in the broadest sense when n tends to infinity will be equal to plus infinity. And repeat on the condition that must hold: for any real number k as large as we want, there exists capital N that belongs to the natural numbers, and for any natural n that is greater than capital N, we will get that an is greater than k. That is to say, from the index n onwards, we have infinite terms of sequence n that obey to this condition. Okay, so we have infinite terms of sequence n that obey to this condition, and that is the reason that the limit of sequence n when n tends to infinity is equal to plus infinity. So the meaning of this condition is that eventually the terms of sequence n are larger than any fixed k. Why? Because from the index n onwards we have infinite terms of sequence n that are greater than k, and that is the reason that the limit of sequence n in the broadest sense when n tends to infinity is equal to plus infinity. So symbolically we can write down that the condition that must hold as follows. For any real number k as large as we want, there exists, this is the sign of exist, capital N that belongs to the natural numbers, and for any natural number n that is greater than capital N, we will get that n is greater than k. Okay? Here n belongs to the natural numbers. Okay? For any natural number n that is greater than capital N, we get that n is greater than k. That is to say, until the index n, we have fixed terms of sequence n that may not obey to this rule, to this condition. But because of the fact that from the index n onwards, we have infinite terms of sequence n that obey to this condition, for that reason we can say, or in other words, we have infinite terms of sequence n that are greater than k. For that reason we can say that the limit of sequence n when n tends to infinity in the broadest sense, it is equal to plus infinity. Okay, so in order that the limit of sequence n when n tends to infinity will be equal to plus infinite, actually infinite terms of n must be greater than k. And k is a large number, as large as we would like. Okay? So, in the next step, I will present to you an example of a sequence that its limit in the border sense is equal to plus infinity. Actually, here we are talking about the set of the natural numbers. We can present the set of the natural numbers according to this formula that n equals to n. When the index n equals to 1, we will get the value of the first theorem, that is to say a1, it is equals to 1. When the index n equals to 2, then the value of the second theorem, that is a2, it will be equal to 2. When the index n equals to 3, then the value of the third theorem of the set of the natural numbers, that is to say a3, is equals to 3. When the index n equals to 100, then the value of the 100th term, that is to say A100, equals to 100. And finally, when the index n equals to n, then we get that an, the value of the term is n. So that is the set of the natural numbers, or the sequence of the natural numbers. It's very easy to see that as the index n increases, the value of the terms also increasing. So we can assume that the limit of the set of the natural numbers, that is to say the limit of an that is equals to n when n tends to infinity, it is equals to plus infinity. Okay? So now we have to prove that the condition that must hold here indeed holds, and for that reason the limit of sequence an when n tends to infinity is equals to plus infinity. So the condition that must hold in order that the limit of the set of the natural numbers when n tends to infinity will be equal to plus infinity is as follows. For every real number k as large as we would like, there is a natural number capital N, and for every natural number n that is greater than capital N, we will get that an is greater than k. That is the condition that must hold in order that the limit of the set of the natural numbers when n tends to infinity is equal to plus infinity. Okay? So, in order to prove that this condition holds, we have to choose the right value of capital N, and we conclude from the value that we choose for capital N that this condition indeed holds. So we will choose capital N that is equals to the integer value of k plus 1000 when it is rounded up. Here, for example, if the number 5.5 is rounded up, then it is will be equal to 6. Okay. And the formula that presents the terms of the natural numbers is an equals to n. An equals to n. So for every n that is greater than capital N, and we choose capital N that is equals to the integer value of k plus 1000 when it is rounded up. Okay, so this inequality is true according to our choice. We choose n that is greater than capital N, and therefore this inequality is true. And we know that an equals to n because this is the formula for the terms of the set of the natural numbers, and we also choose capital N that is equals to the integer value of k plus 1000 when it is rounded up. So from this inequality that is true, we can derive that an is greater than the integer value of k plus 1000 when it is rounded up. But if an is greater than k plus 1000 to the, if an is greater than the integer value of k plus 1000 when it is rounded up, let alone that an is greater than k. Actually, in conclusion, we actually proved that if we choose capital N that is equal to the integer value of k plus 1000 when it is rounded up, then the condition holds. That is to say, we will get that an is greater than k. So this condition holds. If we choose capital N that is equal to the integer value of k plus 1000 when it is rounded up. Because if we get that an is greater than k. That is to say, from the index n onwards, we will have integer infinite terms of sequence an is equal to n, infinite terms of the set of the not one numbers that are greater than k, and therefore we can say that the limit of the set of the not one numbers, that is an equals to n, when n tends to infinity, is equals to plus infinity. Okay. So, in the next step, we talk about sequences that has the limit of minus infinity when n tends to infinity. So, similarly, we say that a sequence tends to minus infinity. So, sequence, the limit of sequence an when n tends to infinity, it will be equal to minus infinity, or we can write down the same thing here, an with the right arrow, that is equals to minus infinity, only if the following condition holds. And the condition that must hold is as follows: for every real number k as small as we would like, there is a natural number capital N, such that for every natural number n that is greater than capital N, we will get that an is smaller than k. That is to say, the condition that must hold is that for every real number k as small as we would like, there exists natural number capital N. So for every natural number n that is greater than capital N, we get that an that is smaller than k. That is to say, from the index n onwards, we have infinite terms of sequence an that are smaller than k, and for that reason we can say that the limit of sequence an in the broadest sense when n tends to infinity is equals to minus infinity. Why? Because we have eventually we have actually infinite terms of sequence an that are smaller than any fixed k, and that is the reason that the limit of sequence an in the broadest sense when n tends to infinity will be equal to minus infinity. Okay, so symbolically, we can write down the condition that must hold as follows. Here, for every k that belongs to the real number, so for every real number k there exists, this is the sign of exists, not one number capital N, it belongs to the not one numbers. So for the not one number N, that is greater than capital N, we will get that AN is smaller than K. Okay? Repeat again. From the index N onwards, we have infinite terms of sequence AN. Therefore, we have infinite terms of sequence AN that are smaller than K. And for that reason, we can say that the limit of sequence AN in the broadest sense, it is equal to minus infinity. Okay, so in the next step, I will talk about the arithmetic of a limit. Repeat again, we will talk about the arithmetic of limits. So if the limit of sequence AN when n tends to infinity exists, and the limit of sequence Bn when n tends to infinity is also exists. So if the limits of sequences AN and BN are both exist, then the following equations will be true. According to equation number 1, the limit of sequence AN plus BN when n tends to infinity will be equal to the limit of sequence AN when n tends to infinity plus the limit of sequence Bn when n tends to infinity. So I'll explain the meaning of equation number 1. In the left side of equation number 1, we have in the first step we will add the terms of sequence AN with terms of sequence BN correspondingly. In the next step we will calculate the limit. So in this way we created actually a third sequence. In the next step we calculate the limit of the third sequence that we created here, and the limit of the third sequence that we created must be equal to the right side of equation number 1. What is written in the right side? Here we will calculate the limit of sequence an separately when n tends to infinity. We calculate the limit of sequence bn when n tends to infinity separately. Then we will add the two limits to each other, and the final result must be equal to the limit of the first sequence that we created here, that is in the right side of equation number 1, when n tends to infinity. Then we have also equation number 2 that is also true. According to equation number 2, the limit of sequence an minus bn when n tends to infinity is equals to the limit of sequence an when n tends to infinity minus the limit of sequence bn when n tends to infinity. Okay. So I will explain the meaning of equation number 2. On the left side of equation number 2, in the first step here, we will subtract the terms of sequence bn from terms of sequence an correspondingly. In this way, we will create a third sequence. Then we will calculate the limit of the third sequence that we created, and the result must be equal to the right side of equation number 2. What is written in the right side of equation number 2? Here we will calculate the limit of sequence an separately when n tends to infinity. We will calculate the limit of sequence bn separately when n tends to infinity. And then we will subtract the limit of sequence bn that we got from the limit of sequence an that we got, and the final result must be equal to the limit of the first sequence that we created here in the left side of equation number 2 when n tends to infinity. Okay, and also equation number 3 that is true. According to equation number 3, the limit of sequence c times an when n tends to infinity equals to c times the limit of sequence an when n tends to infinity. I will explain the meaning of question number 3. In the right side of equation number 3, here actually we calculate the limit of sequence c times an when n tends to infinity, and the result must be equal to the limit of sequence an when n tends to infinity. So we'll calculate the limit of sequence an separately when n tends to infinity, and we will multiply the result by c. And the final result here in the right side of equation number 3 must be equal to the limit of sequence c times an when n tends to infinity. And we have also equation number 4 that is true. According to equation number 4, the limit of sequence an times bn when n tends to infinity is equals to the limit of sequence an when n tends to infinity times the limit of sequence bn when n tends to infinity. So I'll explain the meaning of equation number 4. In the left side of equation number 4, here we will actually multiply the terms of sequence AN by the terms of sequence BN correspondingly, and then in this way we created a third sequence. In the next step we'll calculate the limit of the third sequence that we created when n tends to infinity, and the result must be equal to what we have here in the right side of equation number 4. What we have in the right side of equation number 4, here if we calculate the limit of sequence AN separately when n tends to infinity, we calculate the limit of sequence BN separately when n tends to infinity, and then if we multiply the two limits that we got here, the result must be equal to the limit of the first sequence that we created in the left side of equation number 4. So the two limits here must be equal. And we have also equation number 5 that is true. According to equation number 5, the limit of sequence AN over BN when n tends to infinity equals to the limit of sequence AN when n tends to infinity over the limit of sequence BN when n tends to infinity, provided that the limit of sequence Bn when n tends to infinity must not equal to 0. Why? Because in the denominator of this expression we have the limit of sequence Bn when n tends to infinity, and if the limit of sequence Bn when n tends to infinity equals to 0, then it will comes out that we are actually dividing the denominator by 0, and it is not allowable to divide anything by 0. Therefore, the limit of sequence Bn when n tends to infinity must not equal to 0. And finally, we have equation number 6. That is also true, and according to equation number 6, the limit of sequence AN to the power of P when n tends to infinity must be equal to the limit of sequence AN when n tends to infinity raised to the power of P. I will explain the meaning of equation number 6. In the left side of equation number 6, we have sequence AN to the power of P. So we will calculate the limit of sequence AN to the power of P when n tends to infinity, and the result must be equal to what is written in the right side of equation number 6. And what is written in the right side of equation number 6, here we will calculate the limit of sequence AN when n tends to infinity separately, and then we will raise the result that we got for the limit of sequence AN when n tends to infinity. We'll raise the result to the power of P, and the final result here must be equal to the limit of sequence AN to the power of P when n tends to infinity. Okay, so in the next step, I'll summarize the lecture. So in this lecture we talked about the limit of a sequence. So as I mentioned at the beginning of the lecture, a sequence is a set of numbers, and a sequence can be finite, like this sequence that consists of only 3 terms, but a sequence can be also infinite, like the set of the natural numbers that consists of infinite terms. So we write down that the limit of sequence a(n), lim is abbreviation for limit, n is the index of the sequence, and a is the value of the term that is n, index is n. So here, when the index n equals to 1, in this sequence that is the set of the natural numbers, the value of the term is 1. When the index n equals to 2, then a2 equals to 2. When the index n equals to 3, then a3 equals to 3, etc., etc. So if sequence a(n) and n tends to infinity as a limit, that is to say, if its limit is L and L is also the real numbers, it could be any real number, then we will say that sequence a(n) is convergent. And if a sequence has a limit, it must be the only limit. That is to say, if a sequence has 2 different limits, then it doesn't have a limit at all, and therefore it will be a divergent sequence. So a sequence that doesn't have a limit, like sequence bn, then it will be defined as a divergent sequence. Okay. So what is the definition of a sequence? Here the limit of sequence a(n) and n tends to infinity equals to L. L belongs to the real numbers. We can write down the same thing in another way, a(n) with the right arrow, that is equals to L. Those two expressions have the same meaning. The meaning of those two expressions is that the limit of sequence a(n) when n tends to infinity equals to L. L belongs to the real numbers. The condition that must hold in order that the limit of sequence a(n) when n tends to infinity will be equal to L is as follows. For every epsilon that belongs to the real numbers that is greater than 0, that is to say, for every epsilon that is a positive number, we must have a capital N that is also a natural number, and for every natural number n that is greater than capital N, we will get that the absolute value of a(n) minus the limit L is smaller than epsilon. So graphically we can describe the condition that must hold here in this drawing. Here, if L is the limit of sequence a(n) and n tends to infinity, here L is at this point, then the environment of L starts from L minus epsilon, and the point L minus epsilon is not included in the environment, and ends at point L plus epsilon. But the point L plus epsilon itself is not included in the environment of L. Okay, so this is the environment of the limit L, and the radius of the limit L is epsilon. Okay. From L plus epsilon, we have the radius epsilon. Okay, so here until the index n, we have fixed numbers that don't obey to this rule or to this condition. But because of the fact that from the index n onwards, we have infinite terms that obey to this rule. That is to say, we have infinite terms of sequence an that are located that are in the environment of L, or that are located inside those two brackets. For that reason, we can say that the limit of sequence an when n tends to infinity is equals to L. And again, L belongs to the real numbers. Here we are talking about finite limits. Okay, and symbolically, we can write down the condition that must hold as follows. For every epsilon that is greater than 0, there exists a capital N that belongs to the natural numbers. So for every n that is n also belongs to the natural numbers, for every n that is greater than capital N, we will get that the absolute value of an minus L is less than epsilon. Okay, I'll repeat again. In order that a sequence will have a limit, infinite terms of the sequence, for example here, sequence an must be in the environment of L. That is to say, infinite terms of sequence an must be located between those two brackets in order that the limit of sequence an will be equal to L when n tends to infinity. Then I gave you an example of a sequence that its limit is 0 when n tends to infinity. Here we have the sequence an that is equals to 1 over n. When the index n equals to 1, then the value of the term is 1 over 1. When the index n equals to 2, then the value of term a2 is 1 half. When the index n equals to 3, then the value of the third term of this sequence is 1/3. And the value of the index n equals to 100, then a100 equals to 0.01. So you can see here that when n increases, the terms of the sequence are getting closer and closer to 0. Therefore, we can assume that the limit of sequence an when n tends to infinity is equals to 0. So we have to prove that this condition holds in order that the limit of sequence an when n tends to infinity will be equal to 0. So the condition that must hold is as follows. For every epsilon that is greater than 0, and for capital N that belongs to the natural number, so for capital N that is big enough, we get that for every natural number n that is greater than capital N, we get that the absolute value of 1 over n minus the limit 0 is less than epsilon. Okay, so here the absolute value of 1 over n minus 0 is equal to the absolute value of 1 over n, because when you subtract 0 from something, it changes nothing. So we can cancel out 0. Okay, and the absolute value of 1 over n equals to 1 over n. Why? Because n is a natural number, natural positive number, and 1 over n must be a positive number, because n is a natural number, natural positive number, and we know that the absolute value of a positive number equals to the positive number itself. That is to say, the absolute value of the positive number 1 over n will be equal to 1 over n. And the absolute value of 1 over n minus 0 must be less than epsilon. Okay? So here, this inequality 1 over n is smaller than epsilon must be true. We have to prove that this inequality is true. We have to prove again that the inequality 1 over n is smaller than epsilon, it is true. So here we multiply this inequality by n, we'll get that 1 is smaller than epsilon times n. We divide this inequality by 0, and we'll get that n is greater than 1 over epsilon. So we have to prove that n is bigger than 1 over epsilon. So in order to prove that this inequality is indeed true, we'll choose capital N that is greater than 1 over epsilon, and for every natural number n that is greater than capital N, we choose already that capital N is greater than 1 over epsilon. So this inequality is true according to our choice. So from this inequality, from this true inequality, we can derive that n is greater than 1 over epsilon. That is to say, the condition that must hold, or the inequality that we have to prove that is true, we prove that this inequality is indeed true. Okay? So as already mentioned before, we have the right to choose n that is greater than capital N. Here we divided this true inequality by n, and we got that 1 is greater than capital N over n. Then we divided this inequality by capital N, and we got that 1 over n is smaller than 1 over capital N. We have already proved that 1 over n minus 0, the absolute value of 1 over n minus 0 is equals to the absolute value of 1 over n, and we have already proved that the absolute value of 1 over n is equals to 1 over n. We just right now proved that 1 over n is smaller than 1 over capital N, so we can write here, you can copy this inequality here, and then we focused on the expression 1 over capital N. Here, if we have, for example, the number 1/5, and if we don't change the numerator, we leave it as it is. So here we have in the numerator 1, so we leave the numerator as it is. Here it is equals to 1. But the only change that we will do here will decrease the denominator from 5 to 4. When you decrease the denominator of a number, then the number itself will be greater. As you can see here, we decrease the denominator from 5 to 4, and the number that we got here, 1 over 4, is greater than 1 over 5. So if we decrease the denominator here from capital N to 1 over epsilon, we get that the number that we created here is bigger than the original number, 1 over capital N. And indeed, we know that 1 over epsilon is smaller than capital N. That is to say, when we substituted 1 over n by 1 over epsilon, we decreased the denominator, and when you decrease the denominator, the original number will be greater. That is to say, 1 over epsilon will be greater than the original number, 1 over capital N. And again, when you decrease the denominator, the original number will be smaller than the new number that you created here. So we decrease the denominator from capital N to 1 over epsilon. Therefore, the new number that we created here will be greater than the original number, 1 over capital N. And what is the value of 1 over epsilon? It is epsilon. So we actually proved that if we choose capital N that is greater than 1 over epsilon, then for every n that is greater than capital N, we will get that the absolute value of 1 over n minus 0 will be smaller than epsilon. That is to say, the condition that must hold indeed holds, and for that reason, if we choose capital N that is greater than 1 over epsilon, and for that reason we actually proved that for any epsilon that is greater than 0, if we choose capital N that is greater than 1 over epsilon, then for every N that is greater than capital N, we will get that the absolute value of 1 over N minus 0 is smaller than epsilon. That is to say, we actually proved that the condition that must hold in order that the limit of sequence an equals to 1 over n when n tends to infinity is equals to 0, the condition that must hold indeed holds, and for that reason the limit of sequence an equals to 1 over n when n tends to infinity is indeed equals to 0. Okay? So we finished to talk about sequences that have finite limits. In the next step, actually, we talked about sequences that have infinite limits, or they have a limit in the broadest sense, and their limit is infinite. So here, the sequence an when n tends to infinity will be equal to plus infinity, or we can write down the same thing in another way, that an with the right arrow equals to plus infinity. So the condition that must hold in order that the limit of sequence an in the broadest sense when n tends to infinity will be equal to plus infinity is as follows. For every k as large as we would like, there exists capital N that belongs to the natural numbers. So for every natural number n that is greater than capital N, we will get that an is greater than k. And because of the fact that until the index n we have fixed terms that may not obey to this condition, but from the index n onwards, we have infinite terms that obey to this condition. We have infinite terms of sequence an that are greater than k. And for that reason, the limit of sequence an when n tends to infinity in the broadest sense will be equal to plus infinity. So symbolically, we can write down the limit that must hold as follows. For every k as large as we would like, for every number k as large as we would like, there exists capital N that belongs to the natural numbers. So for every natural number n that is greater than capital N, we will get that an is greater than k. Again, we actually, if this condition holds, we actually proved that we have in sequence an infinite terms of sequence an are greater than any large number k as large as we would like, and for that reason the limit in the broadest sense of sequence an when n tends to infinity is equal to plus infinity. Okay, then I presented to you an example of the set of the natural numbers, and we actually proved that the limit of the set of the natural numbers when n tends to infinity is equal to plus infinity. We can present the natural numbers according to this formula that an equals to n. When the index n equals to 1, then a1 equals to 1. When the index n equals to 2, then a2 equals to 2. When the index n equals to 3, then a3 equals to 3. When the index n equals to 100, then a100 equals to 100, etc., etc. When the index n equals to n, then an equals to n. So an equals to n is the formula that will help us to present the natural numbers. Okay? So we will prove that the limit of sequence an equals to n, that is to say the limit of the set of the natural numbers when n tends to infinity equals to plus infinity. So we have to prove that the condition holds, and for that reason the limit of the set of the natural numbers when n tends to infinity equals to plus infinity. So the condition that must hold is as follows. For every real number k as large as we would like, there exists capital N that belongs to the natural numbers. So for every natural number n that is greater than capital N, we will get that an is greater than k. Okay? So we have to prove that this condition holds. In order to prove that this condition holds, we will choose capital N that is equal to the integer value of k plus 1000 when it is rounded up. For example, if the number 5.5 it is rounded up, we get that is equal to 6. Okay? So here we know that an equals to n, that is the formula for present in the terms of the natural numbers. So for every n that is, for every natural number n that is greater than capital N, and capital R also belongs to natural numbers, and we choose capital N that is equal to the integer value of k plus 1000 when it is rounded up. So this inequality is true according to our choice. First of all, n equals to n, because this is the formula that presents the natural numbers, and n is greater than capital N because we choose n that is greater than capital N. When we choose capital N, that is equal to the integer value of k plus 1000 when it is rounded up. So this inequality is true according to our choice. From this inequality, we will derive that an is greater than the integer value of k plus 1000 when it is rounded up. Okay? So if an is greater than the integer value of k plus 1000 when it is rounded up, let alone that an is greater than k. So we actually proved that if we choose capital N that is the integer value of k plus 1000 when it is rounded up, that the condition holds. We will get that an is greater than k. So actually proved that we, from the index n onwards, we have infinite terms of the set of the natural numbers that are greater than k, and k is as large number as we would like. And because of the fact that we have infinite terms of the set of the natural numbers that are greater than k, for that reason the limit of the set of the natural numbers in the broadest sense, it is equal to plus infinity. Again, the limit of the set of the natural numbers, that is n equals to n, and n tends to infinity, equals to plus infinity. Okay? Then we talked about sequences, that their limits in the broadest sense is equal to minus infinity. So a sequence an, the limit of sequence an and n tends to infinity will be equal to minus infinity, or we can write down the same thing in another way, an with the right arrow equals to minus infinity. Okay? So only if the following condition holds, we can say that the limit of sequence an when n tends to infinity equals to minus infinity. The condition that must hold is as follows. For every k that belongs to the real numbers and as small as we would like, there exists capital N, and for every natural number n that is greater than capital N is also belongs to the natural numbers, of course. For every n that is greater than capital N, we will get that an is smaller than k. That is to say, the condition that must hold, the meaning of the condition that must hold is that from the index n onwards, we have infinite terms of sequence an that are smaller than k. And k itself is the small number as we would like. And because of the fact that we have in sequence an infinite terms that are smaller than k, for that reason the limit of sequence an in the broadest sense when n tends to infinity will be equal to minus infinity. So symbolically we can write down the term that must hold as follows. For every k, or for every real number k as small as we would like, there exists capital N that belongs to the natural numbers. So for every natural number n that is greater than capital N, we will get that an is smaller than k. I repeat again, that the meaning of this condition is that must hold is that from the index k onwards, we have infinite terms of sequence an that are smaller than k. And for that reason, the limit of sequence an in the broadest sense, when n tends to infinity, will be equal to minus infinity. Then we talked about the arithmetic of limits. So if sequence an when n tends to infinity, if the limit of sequence an when n tends to infinity exists, and if the limit of sequence bn when n tends to infinity exists, so in other words, if the limit of sequences an and bn they are both exist, then the following equations will be true. The limit of sequence an plus bn when n tends to infinity will be equal to the limit of sequence an when n tends to infinity plus the limit of sequence bn when n tends to infinity. According to equation number 2, we will get that is true, that the limit of sequence an minus bn when n tends to infinity equals to the limit of sequence an when n tends to infinity minus the limit of sequence bn when n tends to infinity. And we have equation number 3 that is also true. The limit of sequence c times an when n tends to infinity equals to c times the limit of an when n tends to infinity. And we have equation number 4 that is also true. The limit of sequence an times bn when n tends to infinity equals to the limit of sequence an when n tends to infinity times the limit of sequence bn when n tends to infinity. And we have equation number 5 that is also true. The limit of sequence an over bn when n tends to infinity equals to the limit of sequence an when n tends to infinity over the limit of sequence bn when n tends to infinity. Provided that the limit of sequence bn when n tends to infinity must not equal to 0. Why? Because if the limit of sequence bn when n tends to infinity will be equal to 0, then in the denominator of this expression we will have 0, and it is not allowable to divide anything by 0. Therefore, the limit of sequence bn when n tends to infinity must not equal to 0. And finally, we have equation number 6. And equation number 6, according to equation number 6, that is true, that the limit of sequence an to the power of p when n tends to infinity equals to the limit of sequence an when n tends to infinity. And after we will find out the limit of sequence an when n tends to infinity separately, we will multiply the result to the power of p, and the result must be equal to the limit of sequence an to the power of p when n tends to infinity. Okay, thank you very much.